Today on Signal Galaxies Unlimited, we're going to look at spectral painting, otherwise known as making images with spectrograms. If you've attended any of the conferences or conventions, perhaps you've come across spectrograms such as this one that I captured from ShmooCon 2023, or this one at GRCon in 2025, or perhaps you've come across YouTube videos such as Moonshine Radio's video showing this.
Transmitter. This is a red pitaya clone made in China.
Regardless, I'm going to walk you through the theory behind how all of this works, and then I'm going to turn you over to Paul Main, the SDR guy, and who's going to walk you through some of the more practical aspects of how to actually make it work with real SDRs. Before we get started, I want to explain what is the key ingredient of how this all works. That key ingredient is the fact that we are going to be building this image in the frequency domain. Normally, when we think about working with signals and signal processing, we're operating in the time domain. When we think of frequency domain, we think of things such as filtering and so on. No, in this particular case, we're going to be building in the frequency domain. We're going to be building signals based on their frequency, not based on their time domain content. And this is exactly the same way that OFDM, orthogonal frequency division multiplexing, works. So again, we're going to be building in the frequency domain, and then we're going to be converting it, transforming it into the time domain for actual transmission. First things first, the thing you have to understand about how we're going to make an image in a spectrogram is we're going to start with a grayscale image. Understand that when you're making spectral paintings using a spectrogram, it only works with grayscale images. So that's what we're going to start with. I have this old clip art of a rocket ship, and it's a relatively small image. It's only 759 by 433 pixels. But what you're seeing is each one of these pixels has a particular value between 0 and 255, with 0 being black, 255 being white, and then the values in between being these various shades of gray. And if you look at it from a three-dimensional point of view, it will look something like this, where you have, again, the white shown here at the top, black here at the bottom, and then the gray is somewhere in between. And if I pull out, say, one line, let's say along here at line 250, what I will get is something that looks like this. Again, here's the white, here's the black, here's various shades of gray in between. And what we're going to do is we are going to say that these amplitudes are the amplitudes at certain frequency points in our spectrum. And we're going to say that this is where I said we're building it in the frequency domain, and then we're going to transform this into the time domain via the inverse FFT. In other words, we're going to use not the forward FFT, but the reverse FFT in GNU Radio in order to actually build this signal. And we're not just going to do this one signal over and over again. We're going to enter each line individually, and we're going to put that through the reverse FFT, and then we'll continuously transmit that out. So in other words, each line is going to come in, go through the reverse FFT, get attached to the line that came before it, and it gets transmitted out. And that's how we're going to create this signal. I've created this basic flow graph that takes the one line from the rocket ship image, that line 250, and I'm going to pass it through a reverse FFT. That's what this block here is doing, is it's taking the information coming in, and it is saying, okay, this is frequency domain data. I am now going to turn it into time domain data. And then it's going to show us what it looks like in both the time domain and in the frequency domain. So first, when we run this, initially what we're looking at is we're looking at the actual original line itself. This is the one that should appear just as it did before, where I've got 255, the white here at the top, black here at the bottom, and the various shades of gray in between. And when you look at the spectrum, this is what the spectrum looks like. And you notice that we now have, again, I'm looking at the spectrum, so notice that looks pretty much similar to what the original signal looked like, because again, I'm treating it as frequency domain data, and then I'm transforming it into the time domain data. However, there is an issue here. The big issue is that if I do not do anything with the data before it passes through the inverse fast Fourier transform, in other words, if I do not change it before it goes through the reverse FFT, what's going to happen in the time domain is it will look something like this, where I have all of the energy bunched up into essentially one clump. This harks back to the old adage of if you have a square pulse in one domain, you're going to wind up with a sin x over x in the other domain. This is exactly that. Notice that when you're looking at our original signal, I have a lot of pulses here, and that all clumps up into this one big sin x over x curve with very thin main lobes here, and which means that it's going to be clumped up into the one big part of time. And the problem is that when this passes through the spectrum, when this goes into the spectral display, what's one of the first things that it does? It gets windowed. What does the window do? It pushes the ends towards 0. Therefore, if I were to apply windowing, right now I have the windowing turned off, but if I turn the windowing on, I'm going to go ahead and do that. Going from rectangular, I'm going to go to the usual one in GNU Radio, which is Blackman-Harris. When I turn that on and run it, original signal looks just fine, but now my spectrum looks kind of like crap. And again, that's due to the fact that I have all of the energy clumped up at the ends, and so the window is going to have a really bad effect on it. Therefore, one of the things that I want to do is in the original signal, I'm treating each of these points as a frequency point. That's the way that I'm treating it. But I'm only affecting the amplitude or magnitude. I haven't touched the phase. I'm assuming the phase for all of these zeros is 0, which means that all of the phases are literally lining up because all of these frequency points are harmonically related. Therefore, I need to screw up. I need to remove that phase alignment, that phase coherency between the frequency points. To do that, what I have done is down here at the bottom, I have added in a little circuit here that will randomize the phases of each frequency point individually. It's just going to essentially create, think of this as a really large phase shift keying signal. In this particular case, I'm doing phase shift keying over 128 points because the point is not to actually transmit information with the phase. The point is just to get rid of the phase coherency. And to do that, that's what this does so that none of the phases will really line up. Coming back to my original signal, once I invoke the phase coherency, that's what this little randomization button does. When I turn it on, notice that, yes, I've got this noise on the peaks of my signal now, but when you look at it compared to the original signal, it looks a lot more like it did before. The next thing that I want you to notice is that when you look at this original signal, you notice I got 255, 255 across the top, and then it drops down by about, let's say, a fifth. However, when you look at the spectrum, it's really high, really high, really high, and then it drops down only a little bit. That is due to the fact that we're dealing with a logarithmic scale, whereas the original signal is on a linear scale. Therefore, what I'm going to show you is I'm going to show you a circuit that I created that will do several things. First off, it's going to randomize the phase. It will also pre-warp or pre-adjust the amplitudes of the signal such that when they pass through the spectral display and get displayed on a logarithmic scale, they'll actually be more linear from a visual standpoint. And then from there, we'll be able to actually transmit it out, look at it on a spectrogram, and see how it looks. Before I jump into GNU Radio, let me explain how I'm going to actually make the file that we're going to import into GNU Radio. We're going to start with using GIMP. When you're using GIMP, the reason that we're using GIMP or some of these other tools is the fact that GNU Radio Companion cannot handle the image files directly. In other words, you cannot feed it a JPEG, a TIFF, a GIF, a PNG, a WebP, whatever. You have to convert it into straight two-dimensional array of values, preferably the 8-bit values for 0 to 255, again, because you need to feed it a grayscale image. So what I have here is I have my original rocket ship logo here in GNU Radio, or here in GIMP, and what I'm going to do is there's three things that I want to potentially do in GIMP. The first thing that I probably want to do is I want to maybe resize the image. So if this image was not the right size that I wanted for whatever reason, I would come up and I would click on image and then scale image, and then I would use these adjustments here to set the value to whatever width or height, whatever you wanted to do manually, and then click scale and you're done. This particular case, I want the image to go ahead and stay the same size that it is. The next thing that I might want to do is I might want to set it to, or no, I will want to set it to grayscale. So the next thing that I will do then is I will come up here and I will click on image, and then I will click mode, and then I will say grayscale. It's already in the mode, but if it was a color, it would probably be an RGB mode. I'm going to click it grayscale. That will turn it into the grayscale as needed, and I'm good to go. The third thing that I might need to do depends on the spectrogram that it's going to be drawn on. If I'm going to be putting this onto a rising waterfall, a rising spectrogram, such as you find in GNU Radio Companion itself, then I don't need to do anything with the image. I'm good to go. If, however, I'm going to be showing it on a falling waterfall, a falling raster, a falling spectrogram, such as you find in SDR++, SDR Angel, most of your popular SDR programs, then I will probably want to flip the image vertically. To do that in here, I'm going to come up here, I'm going to click on image, and then I'm going to click on transform, and then click flip vertically. That way it's good to go. So this is how I would want to import it into the GNU Radio Companion flow graph that I'm going to show you. Export it as whatever format, whether it's going to be straight through an SDR or into a WAV file, which I will then import directly into that program, whatever form that you're going to do that. Regardless, those are the three things that I'm going to possibly do with GIMP. Again, the only thing that I really need to do is I need to make certain that it is in grayscale format. Otherwise, I might want to rescale it, resize it, and or I might want to flip it vertically. The last thing, once I've got everything set up the way I want it, I'm going to export it. To do that, I'm just going to click on File and then say Export As. Navigate to wherever I want to put it, and then I'm just going to go ahead and give it a name. I'm going to say Rocket Ship. I'm going to go ahead and put in the width of the image in pixels. I'm going to say 759 points. That's going to be important when I import it into the GNU Radio Companion flow graph. And I'm going to say width, and then I'm just going to put .raw, a raw file. A raw file in GIMP means that it is going to export it straight as a two-dimensional array with no metadata buried inside of the file. It's not going to do any compression, so it's going to be purely lossless. And with that, I go ahead and click Export, leave. It'll have a little pop-up window. Leave the defaults, click Export, and you're good to go. To demonstrate this with another color, an actual color image, this is one that showing Lucerne, Switzerland, and the Reuss River. And what I'm going to do is, the first thing I might want to do is, this is an awfully large image. It's 5312 by 2988. I might want to drop that down a little bit. Now, to be clear, if I wanted to, I could leave this as is. The formats, the flow graphs that I'm going to show you, the tools that I'm going to show you can handle this size, but it's going to be an awfully large image file-wise, so maybe you want to drop it for whatever reason. So I'm going to click on image, I'm going to say scale image, and then I'm going to say drop it down to, let's say, a 1600 width. It automatically adjusts the height to make it 900. I'm going to say scale, and there we go. It's now set the size that I want it. The next thing I'm going to do is I'm going to go ahead and say grayscale. I'm going to say image mode grayscale. Boom, that part's done. Let's say that I'm going to import this into SDR++. In this particular case, that means it's a SDR++ uses a falling waterfall, which means that I would want to flip this. So I'm going to click on Image, Transform, Flip Vertically. There, it's now ready for export. I'm going to click on File, Export As, And I'm going to go ahead and say, just leave it the Lucerne River. I'm going to say 1600 point width. And I'm also going to add flipped, just to be clear, and then .raw. Export, the little pop-up window, leave the defaults, click export, done, and now it's ready to import into the GNU Radio Flow Graph for actual transmission as a spectral painting. Another way that you can transform the images into something that GNU Radio can handle is using an Octave script. I've actually provided two. One will keep the image upright, the other one will flip it vertically if you're dealing again with the falling waterfall type spectrograms. The way that this works is you're going to have to put the both the Octave script and the image into your working directory, the current directory as defined in Octave here. And then what you're going to do to run it, you just give it the name. It's going to request the name of the file, so it's rocketship.jpg. And when you run it, what it will do is it will import the image. If it's color, it automatically transforms it into grayscale and then exports it as a unsigned 8-bit integer. That's what this extension .ru8 means. It means it's a real-only unsigned 8-bit integer, what GNU Radio calls a byte format. The other one is does the exact same thing, except it also adds in a vertical flip, and that one is called Jersey Image Flip. And I'm going to do the exact same thing, ship.jpg. It will do, again, if it's in color, it transforms it into grayscale. It flips the image vertically and exports it as a .ru8. And the difference between the first file format, file name, and the second one is obviously it puts in the word flip just so that you know that, hey, that's the one that's been flipped vertically. Note that neither of these scripts will have any effect on the original image. Again, just reads it in, does a little bit of processing on, and exports it as a completely new and different file. Once you have these set and ready to go, then you're ready to import these into GNU Radio and for processing. Let's do that next. I'm now back in GNU Radio here, and I now am looking at the flow graph that I've created in order to take the image and convert it into something that we can then put out onto a spectrogram. Now I've have this particular one set up such that we can use it either to export directly into a SDR, such as a HackRF, a USRP, something like that. Or you can also, if you so desire, you can export it into a file sync. In this particular case, I have it set up for a WAV file sync, which is what many of the more popular programs such as SDR++, SDR Angel, and things such as that, those programs use WAV files, and so it's ready to set up for that. I am going to demonstrate this using SDR Angel, but let's explain what's going on here first. First off, for the file source, I've opened up the file and I've given it the name of that .ru8 that I created with the Octave script. If this was I was going after my raw file created with GIMP, then it's just the difference is I would just go and find the file with the .raw. It's going to be exactly the same either way. Again, those values, those grayscale values, are 0 to 255, which are what in GNU Radio they either call it a byte or an unsigned char. So I'm using this uchar to float to transform it into 32-bit floating point values. That's where all the processing is going to happen. The first thing that I'm doing here is these three blocks do nothing more than pre-distort the amplitude such that when they get displayed on the logarithmic scale of the spectral display, they'll be visually linear. So in other words, it will look correct. Otherwise, if you don't do that, it's going to look very washed out. The next thing that happens is what we talked about earlier, where I randomize the phase. That's what these blocks here are doing, is they are randomizing the phase of each of the frequency points so that all of the energy does not clump up in time and create problems when you're actually trying to display it spectrally. The next thing that I'm doing is I'm zero padding each end of each line of the image. And the reason I'm doing that is that will center the image spectrally. And so when you're looking at it from a standpoint of, I need this to really be a power of 2. Now, The FFT in GNU Radio does not require it to be a power of 2, but your spectral displays typically do. So just to make things easier, I went ahead and made it a power of 2, and that's what this does. This adds enough zeros to each end that the signal will be centered spectrally, and then you have zeros on either end. Here is the actual FFT, but notice beforehand I have this block called repeat. What I'm doing there is that in certain cases your spectrogram might be display the signal very slowly, and if that's the case, then it's going to look squished vertically. In order to get around that, you might need to add a lot of repetition to each line in order to blow it up, to expand it vertically. Now again, this is going to depend on the particular spectrogram, and trying to design it for every possible spectrogram with one repetition value is impossible because there's too many variables involved with how fast a spectrogram updates. Then of course I have the FFT. Notice that the FFT is set for reverse. And the reason it's a reverse is we're doing from the frequency domain. Again, we're building the signal in the frequency domain, then we're transforming it into the time domain. The output there, we're effectively done. I've got the throttle, I'm going into a waterfall sync and a time sync so that you can see what the signal looks like in the time domain as well as in the spectral domain. And again, you can actually see the image. And then I have these other blocks turned off, temporarily disabled because I'm not using them. With that, let's go ahead and see what our image looks like. And what you're seeing here is this is what the time domain signal looks like. You notice that it's got all of the energy is spread out in time, which is the way we want it, but that creates a fair amount of noise in our signal. And if we wanted to make it look cleaner, then what we could do is we could turn off the windowing in the spectral display. So if you have the option to use a rectangular or uniform or boxcar window inside of your spectral display, that might make it look cleaner. Depends on your particular your system though. But notice again, I'm squished vertically. I'm really not seeing the image. So a couple of things that I can try. First thing is, can I speed up my waterfall sync? In the waterfall sync, I have this update period. Let me see if I can make that go faster. I'm going to lower the update period, and let's see what that does. Well, yep, that pretty much does it right there. I'm actually already starting to see, yep, I can see my image as it's being recreated over and over again. The other option, if that was not an option, so if I went back here and I said, okay, maybe that's not something I have real control over, I could come over here and I could say, well, let me increase the amount of interpolation. That will do the same thing. Again, all you're doing is you're just repeating the same lines. Each line's getting repeated over and over again, and it slows down the amount of data that you're going to be, or the amount of time that each line has to draw. So essentially it slows down the update rate, and which then matches what you have for your spectrogram. Last thing that I want to do here while we're in this particular flow graph is I'm going to go ahead and enable the wave file sync. Now when I do this, when I actually create a file, I want to remember that I have this value over here, repeat, set to yes, and I want to change that to no. So when I'm doing this, I want to make certain that I'm actually storing it to a file. I want to make sure the repeat value is set to no. Otherwise, it's going to just run until you tell it to stop, and you end up with a very, 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 very large file. With that, let me go ahead and run this. It's done. And I now have a WAV file that I can then import into other programs to see how it displays. Last thing I want to cover, when you're at first opening up the image, two things that you're going to need to adjust. When you open this up, notice that it says 759 points. First thing that you're going to do is you have to manually come in here and you have to change this value to that 759. The second thing that you want to do, that you might want to do, is you might want to set this value. This is the dynamic range that I'm having it set for in decibels. So I'm saying 40 dB. Most of the people watching this probably don't have really high-end transmit capable SDRs, and so you might in other words, if you're using like a Hack RF1, Hack RF Pro, which only have 8-bit quantizers, you're going to want to set this to probably leave this at 40 dB. If you have, say, a USRP, maybe an Adon Pluto, something like that, you might be able to make this larger. All this affects, though, is the amount of dynamic range that the output image will have when you look at it visually. Okay, so with that, let's go ahead and open up SDR Angel and see how our image looks there. I've opened up SDR Angel, and I'm looking at it because I have currently have no radios attached to my computer. It automatically said, okay, you must want a file input. And with this, I'm going to click on this little icon up here in the upper left-hand corner. I'm going to select the particular file that I want. And I should just be able to run this, and we'll see how it looks. And what you're seeing is you're seeing the spectral display on the top, the spectral trace, and then you have the spectrogram on the bottom. And notice that it is, well, it's showing up quite a bit as a quite stretched vertically. The reason being is that due to the fact that this thing is updating much faster than did the one in GNU Radio. So what I would probably want to do is I'd probably want to go back in and change the repeat value, because if I recall correctly, I had it set to like 10, so I might want to drop it to 5, 3, maybe just leave it at 1, and then it will look more natural. But otherwise, notice that you are getting the original image just the way you want it. Now notice that right now I have the window set to rectangular. I'm going to go ahead and set that to Blackman Harris just so you get a better idea. This is likely what you're more likely to see on your actual image. So with that brings us to an end of this particular video. I'm now going to turn you over to Paul Main, the SDR guy. And he's going to walk you through how to load the various programs that you might want to use to create these images. He's going to walk you through how to make the images themselves, and then he's also going to walk you through actually transmitting with different SDRs. So over to you, Paul, from here. Oh, hey, yeah, hi. I'm just going to slip in a little bonus content for you. Today, some tall sailing ships were sailing up the Chesapeake Bay. The wife wanted to go look at it, so we drove out to Sandy Point State Park, and we saw several of those tall sailing ships. The picture that you're seeing right now is one that I took with my phone, and it's showing the Lady Maryland with the Bay Bridge in the background. And I wanted you to see what is possible with the spectral painting stuff. So I took this particular image, I lowered it to a 1600 by 900 size, converted it to grayscale, and then flipped it vertically, saved it using GIMP, imported it into the GNU Radio flow graph, and saved it as a WAV file. And then I'm now looking at it this is SDR Connect. So this kind of gives you an idea of what is possible. Notice that again, as I said before, it's fairly noisy due to the fact of the windowing. Unfortunately, SDR Connect does not have a no window option. All of the windows are the standard windows, which you can see up here. I've got the Sign 3, the Sign 5, not all flat top, and Blackman doesn't have an option for the rectangular / uniform / boxcar. But regardless, still a pretty cool picture. Again, this is what's possible using spectral painting, spectral image on your spectrogram, and I hope you enjoy that and have fun with it.